We're on page 11. Some various odds and ends that close out Unit 7. First off, let's return to the slide problem. But this time we won't invent a frictionless slide. Let's use a real slide. So first off, go ahead and draw this picture. So here's our slide. There's the ladder. This time we're going to use a different situation. Janie climbs to the top of a 4-meter high slide. So there's 4 meters. Janie, mass 40 kilograms, slides down the slide and reaches the bottom with a velocity of 6.0 meters per second. So 40 kilograms, 6 meters per second. Question is, how many joules of heat energy were produced by Janie's trip? Now you can't just jump to the heat and say this is how much. You have to calculate a couple other things. You have to know the potential energy at the top. This is really the maximum amount of energy that you have. And then we have to measure the kinetic energy at the bottom. This is how much of that potential was actually changed into the velocity. So the potential energy at the top, mgh, mass times acceleration of gravity times the height. So mass 40 kilograms, 10 for gravity, and the height is 4 meters. So the potential energy is 1600. This is the maximum usable amount of energy. We know some of it's going to become kinetic and some of it's going to be heat. So we need to find the difference between these two. So let's look at the kinetic energy at the bottom. We can do this. We have all the numbers. 1/2 times the mass times the velocity, and we're going to square the velocity. This ends up 720 joules. And so let's find the difference between these two. So 880 joules. This is the heat caused by the friction. This is how much energy was not converted into usable kinetic energy. Second thing is the kinetic energy in terms of a pendulum, kinetic and potential energy. When a pendulum is pulled back, it has potential energy. When it's released, the potential energy is changing to kinetic energy. When the pendulum reaches the bottom point, all of the mechanical energy is now in the form of kinetic energy. But as it swings upward, once again, it's regaining some of that potential energy. So your notes should already have this drawn. So the dotted line with the empty circle is the at-rest position, the equilibrium position. It's at the bottom. As we pull the pendulum back, it is increasing potential energy, and then we let it go. So here is our pendulum swinging, and it's just now getting to the bottom point, but it's going to keep going because it has velocity. And compare that with, this was the starting point. Something to remember, the H and potential energy is the vertical distance. And so we have to look at pendulums in a special way. A pendulum bob of mass 2 kilograms on a 2-meter string is pulled back to a 30-degree angle and released. What will its velocity be when it reaches its at-rest position? So first off, we're going to draw a picture. You should always be in the habit of drawing a picture. Okay, so here it is. The length of this entire string is 2 meters. We're going to pull this back to 30 degrees. Remember, the picture is approximate. So there's 30 degrees. Now, the side of this, we're kind of making a triangle right now, is still the length of the string. That hasn't changed. Still 2 meters. Here's what we're going to do. We're going to make a right angle with the equilibrium position. So here's my right angle. And this picture is not turning out very well. Let's see if I can make this a little better. Like that. Okay. So there's my right triangle. The right angle is with the equilibrium position of the string. Here's an important piece of information. H, vertical distance. The vertical distance is not the length of the string. Because if you look, the vertical distance is here. This is how much higher we've lifted it. Now, yes, we've pulled it back, so it's moved a longer distance, but really we've only given it enough potential energy to say that we've increased its height by this much. We're concerned about the increase in the height. So in order for us to figure out this leg of the triangle, it's basically 2 minus h, and we're going to call that one x. So x is, let me change colors here so you can see it better. X is from here to here. And let's do h. Okay. So here's what we want to know. When I pull it back, it has potential energy. All of its energy is potential. And then I let it go, and it is becoming kinetic energy, which has the formula 1/2 mv squared. And we're looking for its velocity. So first off, we want to calculate its potential energy, which means we have to know how high we lifted it. So we can't just go in and figure out h. We have to figure out x first. So here's my 30-degree angle. We have a hypotenuse. X is the adjacent side, which means we have to use the cosine of 30 degrees, which is the adjacent over the hypotenuse. So we find that X is 1.732. Here's the length of the string, and it is the sum of X and H. And when we solve for H, we end up with 0.268 meters. So we've increased the height of this pendulum bob by 0.268 meters. And this is the number that we're going to need when we calculate our potential energy. What is the potential energy of the bob at this point right here? 2 kilograms. Acceleration of gravity is 10. And now the height, 0.268 meters. So the potential energy is 5.36 joules. That's its potential energy here. Now when it gets to the bottom, 100% of that has been changed into kinetic energy. So the kinetic energy at the bottom, 5.36 joules, was 1/2 times the mass times the velocity squared. So we solve for the velocity, and just a quick note, you really don't need to do a whole lot of math here. This 2 and this 2 cancels, so you've got v squared equals 5.36. Square root of that, 2.32 meters per second. This is its velocity when it reaches that at-rest position. I'm going to ask the question first, and then we'll calculate the numbers after that. If the bob is pulled back to a 60-degree angle, will the velocity at the at-rest position change? So I'm going to pull this back farther. Now look at this. I have changed its potential energy even more. More potential energy means more kinetic energy at the bottom. That means, yes, the velocity is going to be higher. Let's draw a picture. It's the pendulum bob, 2 meters. This time we're going to pull it back to 60 degrees. The string is still 2 meters. This is its new height. Has a lot greater height in this one. Yes, we doubled the angle, but the height is much bigger. And then this side is X. So we have a triangle here. We know the hypotenuse. We can find X. So X equals 2.0 times the cosine of 60 degrees. The adjacent side. We're using cosine. So X equals 1. The whole thing is 2 meters, which means H equals 1. So calculating the potential energy, mass is the same. Gravity is the same. And the height this time is 1 meter instead of 0.268. Potential energy is 20 joules. This is its potential energy. It's also its kinetic energy at the bottom. So 20 joules, 1/2, and we know the mass. Kilograms, and we're looking for the velocity. Again, those will cancel out. So we have v squared equals 20, and the velocity equals 4.47, and that's meters per second. Question, will the period of the pendulum change? This goes back to unit 4.5, which we may or may not have done depending on what year this is. For this particular school year, 2021, we did not do it yet. The answer is no. Basically, we're talking about if I pull it back to here, so there's one period. So how long does it take to go out all the way and back? And the question is, will it change? No. Short explanation. So the period of a pendulum is only affected by the length of the string. So you pull it back this far, and it's going to go out and back in a certain amount of time. You might think that pulling it back farther, yes, it's got more to travel, but it's going to be moving faster. This is how much it was traveling in the first scenario. This is how much it was traveling in the second scenario. So yes, there's more distance to cover, but it also has a much higher velocity, and the period is going to remain the same. The only factor is the length of the string. A 500 kilogram wrecking ball on a 20-meter cable pulled back to a 40-degree angle and released. So let's draw our picture here. Here's H, here's X. I know the whole thing is 20 meters. So there's our sketch. A, how much kinetic energy does the ball have at impact? Well, first off, we have to figure out how much potential energy did it have in the first place. So let's go ahead and 5,000 kilograms, 10 meters per second squared, and the height is h. So let's pause and figure out what we have for h. We excuse me. So to find h, it's 20 minus x. We can find x because it's the adjacent side. So the cosine of 40 degrees is x over 20. X equals 20 times the cosine of 40 degrees, and that's 15.32 meters. And now we want to find h. 20 minus that number, 4.68 meters. And we'll put that number in here, 4.68 meters. So this is going to give us a potential energy of 234,000 joules. So we're going to imagine that the equilibrium position is the point where this thing is going to hit the building. For the maximum amount of energy, that's where you would want to hit. So you position the top of the crane directly above, 20 meters directly above what you're going to hit. Because once it goes past that point, it's going to be losing energy. And so the maximum amount of energy is going to be right there at the equilibrium position. Which means that its kinetic energy at this point exactly at the bottom is the same as its potential energy at the top, 234,000. B, what velocity does the ball have at impact? Well, if we know the velocity, we can figure out kinetic energy. So kinetic energy is 1/2 mv squared. We know the energy is 1/2. We know the mass, and there's v squared. Solving this, we have v squared equals 93.6, and square root of all of that, velocity equals 9.67 meters per second. There's your answer right there. Part C, what velocity would your 600 kilogram car need in order to have the same kinetic energy? So 234,000 joules is the kinetic energy. The thing that's changing here is the mass. And we're looking for what velocity? So we solve this, it's v squared equals 780. And so the velocity is 27.9 meters per second. Which, if you think about it, highway speed in the SI system is around 24, 25 meters per second. So this is probably about, approximately 60 miles an hour. A, show that the mass of the pendulum bob does not affect the velocity of the bob in its at-rest position. So here's the potential energy. So there's a big M for mass. Here's gravity. We're using these numbers. So here's the height, 4.68 meters. And so we get 46.8 times the mass, joules. Then for the kinetic energy, 1/2, big M for the mass, v squared. So let me back up and put in this number because that is the kinetic energy. There we go, 1/2 times big M for mass times v squared. And the velocity squared is 46.8 times 2. So here's what happened. Masses cancel out because they're on either side. And so we get 93.6. Square root of that tells us the velocity is 9.67 meters per second. So the mass was constant. We didn't need it here necessarily because it canceled out in the kinetic energy. The last piece is the kinetic and potential energy with a spring. when a mass is attached to a spring that's compressed or stretched, we are giving the system potential energy. When we release the mass, the potential energy turns into kinetic energy. Let's put this in. So here's my at-rest spring. And when I pull it out, something like that, and when I compress it, something like this. So when I stretch it and I let it go, it's changing its potential to kinetic energy. When it reaches the at-rest position, all of the mechanical energy is kinetic, just like with a pendulum. But after it passes this, it's going to keep going until it is back to potential energy. So the formula for potential energy of a spring is 1/2 times kx squared, where k is the spring constant and x is the stretch or compression. So how much potential energy is stored in the system? 3 kilogram mass, spring constant is here. Potential energy is 1/2 times k times x squared. And we'll just plug in our numbers. And when it comes to kinetic energy, this is the potential, this is the kinetic when it reaches equilibrium. We know the mass is 3, and we're looking for velocity, where v squared is 5, and the velocity comes out to 2.236, and that's meters per second.